Good afternoon, class. Today's topic will be section 2.1, set concepts. So this is our first foray into something that for a lot of you may not look like math. Um, so we finished up our algebra and with the exponential notation and the scientific notation. And so now we're going to get into a different style of math. There is no algebra that you think of as algebra. There's very little arithmetic. If you can add and subtract, and if you can raise a number to the second power, you've got the arithmetic in chapter 2. So you have to get a different mindset for both chapter 2 and chapter 3, which is on the next exam. You've heard many times that math is like a foreign language. Well, to be successful in chapter 2 and chapter 3, you have to learn a new language. And very often in learning a new language, the first thing you start out with some basic vocabulary. So that is what section 2.1 and 2.2 for the most part is. And then once you have some basic vocabulary, then you can start creating sentences and paragraphs. And that's sort of like 2.3, 2.4, and 2.5. So I even made a list of vocabulary and typed it all up and put it in Blackboard, which I'll show you in a second. But from 2.1, I came up with 17 definitions. And then there's total of 20, I got a total of 23 by the time I got through 2.3. Okay, so you're definitely going to have to learn definitions and to be successful in chapter 2. And not just learn those definitions, but you need to be able to apply them. Right. And along with that, you need to know the notation as well, because a lot of these ideas we're going to talk about have specific symbols that we use with them, and we're going to use that instead of the wording. And so you have to know what those symbols mean as well. All right, let me show you something. So as always, I'm starting with the stuff I have in Blackboard. Now I have added in the lecture notes, I have added that definition list that I talked about. So chapter 2, set definitions. And so today I'll kind of be going back and forth between that and the 2.1 handout, and I'll also be going into Math Lab. So I'll be doing a little bit more than I usually do in Math Lab, just because there's a lot of, since we're doing a different style of problem, Math Lab is much better a skill practice. The concept stuff, it's a little bit doesn't deal as well with. So there's a lot of multiple choice questions, particularly in 2.1 and 2.2. So I want to make sure that as we're going over the concepts, you also see how MATLAB handles it. And so as we're going through this, you'll definitely see how we're using our definitions. So if you're following along, you probably want both the set concepts and the lecture outlines and the definitions. All right, so let me get into my document camera and then we'll get going. All right. So again, we're going to start off with a bunch of definitions. And so let's just start with the set. And so a set is just a collection of objects. We're in a math class, these sets or these objects are normally going to be numbers, but they could be anything. They could be days of the week, they could be people, they could be types of trees. It doesn't really matter what we're talking about, but a set is just a collection. And one thing with a set, every time we write a set in math, and those are kind of poor curly brackets, but I think you get the idea. So sets are always inside the curly brackets. Sometimes MATLAB, or I would say probably 2/3 of the time maybe, MATLAB puts the curly brackets outside the answer box. Sometimes they don't, so you got to watch for that. I kind of wish they never did, so that way every time you're putting in a set, you're putting in those curly brackets. And that's something that students tend to overlook, I think, in part because MATLAB does it for you. If you have multiple items in the set, you can separate them by commas. If you see a capital letter in front of the set, that is its name. Like A, B, and C, are normal set names, but we could, if we want to name a set, we'll put that in front of it, and that way we don't have to like write out the whole set. We'll just use the letter for the set. Okay, so that is a collection. An element of a set is a single object in that set. So if our set is, say, the days of the week, then one of the elements would be Monday, one would be Tuesday, and so on. The notation for an element, it looks like a C with a bar, sort of like an E C combination. So if X is the element, then you have sort of that curved E/C, and we say A, so that would read X is an element of the set A. And so in that case, like I said, if A is the set of the days of the week, X would be Monday, would be Tuesday, and so on. If you ever see the symbol, anytime we do a slash or something in this chapter, that means not. Okay, so if we wanted to say like Y is not an element of A, or A is days of the week, then Y could be, I don't know, April. April is not a day of the week, so April would not be in the set A, which is the days of the week. And just as a reminder, as we're going through all of this, on that handout for the definitions, I have all of these definitions written out for you, like all in one place. So that way, if you're trying to go back and hunt for them, then they're all in that one document. Okay. So what makes a set well-defined? Well, a well-defined set is where the elements in the set are clearly determined. So that means we know exactly what the elements are. To give you any examples of this, the set of professional baseball players over the age of 39, is that well-defined? Well, yes, because one, we're going to have a list of professional baseball players, and two, we're going to have a list of their ages, so we'll know which ones are over 39. What about the set of people who are expensive perfume? Is that well-defined? Well, it turns out there's one word in here that makes this not well-defined, and that word is expensive. Because what does expensive mean? I have a feeling that what I would think is expensive perfume is probably a lot lower bar than some other people, right? And so since that word expensive makes it not clearly defined, because two people can look at perfume and one person say it's not expensive and another person would say it is, that is not well defined. And so we don't work with sets that are not well defined. What about that next one? Set of birds nesting in trees on Elm Nature Center on March 13th, 2012. So is that well defined? So are all the elements clearly defined? Yes. So we want these birds that are nesting at this spot at this time. Now, can we like actually physically go out there and find every single bird? If it's a large nature center, probably not. But that doesn't mean just because we can't physically like touch them or see them, doesn't mean that we don't know exactly what the elements are. So since we know what the elements are, it is well defined. All right. And once I get into math lab, we'll show you how they kind of handle those. Some other things with sets are finite and infinite. Yeah. So finite sets are where you have I'm going to say we have a limited number of sets, like the days of the week has 7 elements. Days of the year has 365, so as long as there's a specific number of elements, that's finite. Infinite number set has an infinite number of elements. Like basically goes on forever, never stops. Now, the math teacher in me says that, made me put that note, if this was a math class for mathematicians, my above definitions would not work, but that's more than good enough for this class. So let me show you what we need to know about infinite and finite. So if you look at this set, 1 over 4, 1 over 16, 1/64, and then dot, dot, dot. Well, what does that dot, dot, dot? Well, that dot, 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 when we're dealing with our sets, means that we are continuing that pattern, and if it's at the end, it does not end. So this is basically powers of 4, 1 over powers of 4, because that's 4 to the first, 4 squared, 4 third. So we can have 1 over 256 is the next one. And so we can keep going on forever, 1 over powers of 4. That's never going to stop. So that's going to be infinite for us. Now, if you look at the next set, starts at 10, 11, 12. What is that? Dot, dot, dot. Well, that dot, dot, dot means we're going on the pattern that's already established, which usually we need 3 numbers to establish a pattern. So 10, 11, 12, next will be 13, 14, 15, and so on. Where does it stop? It stops at 40. So we could actually count these. So there's going to be from 11 to 40, there would be 30, and then 10 would be 31. So there is a limited number of elements in that set, so this would be finite. And by the way, when you have these numbers listed out like this is what we call roster form. And so roster is just a list of elements. Okay? So put the curly brackets, beginning and the end, you start listing out your elements, put commas in there between each element. Proper elements, we don't list repeats. So if we, like if we had 2 10s in a set, we wouldn't list it twice because we're really listing just the distinct or the unique elements. And also technically order doesn't matter. If I wanted to list the days of the week, like Friday, Wednesday, Monday, Sunday, that doesn't matter either in general, but sometimes MATLAB will tell you to put the elements in order, so watch out for that. But just for normal roster, it doesn't matter who you put first, who you put last, just list everything and don't list repeats. If you list repeats, MATLAB tends to count it wrong. Okay. All right, the other thing you have to be careful of, this really has anything to do with finite or infinite. So if we're going to list out number 8, the set of multiples of 2 between 0 and 50. Okay, so we're going to put this in roster form. Start with your bracket. So what is the first number we're going to list? So do we list 0? Well, if multiples of 2, that's basically saying it's even. Is 0 an even number? Well, -2 is even, 0, 2 is even, 0, so I would say 0 is even, but do we list it? Because it says between. Now, one of the things you have to be careful of, particularly in 2.1, when you're listing out your elements, be careful on the endpoints, especially if it's in sentence form. If we want to include 0, we'd have to say like between 0 and 50 inclusive, or including. And so since there is no inclusive or including language, 0 and 50 are not in this set. Okay, so the first element is going to be 2, and then we're doing multiples of 2, so 2, 4, 6. Now this is where that dot, dot, dot comes in handy because I don't want to list all these numbers. And then since it didn't say we include 50, the last even number before 50 would be 48. And then you do your close bracket. Okay. That would be an example of a finite set. All right, so number 9, the set of natural numbers greater than 100. Okay, well, what are natural numbers? All right, so let's back up. So one of the things, particularly in 2.1 and 2.2, we talk about different sets of numbers. And so natural numbers, I've got all these written out, so I'm not going to write them on this page. So if you get to the definitions page, our handout, natural numbers are what we often call counting numbers. So they start at 1, 2, 3, and then go on forever. Okay, so no fractions, no decimals, no 0, no negative numbers. The notation is a boldface N, or sometimes you'll see the N with like a double leg at the beginning. I don't have a special thing for that, but often it's just bold N, bold capital N. So natural numbers are basically the positive numbers, non-decimals, non-fractions. Whole numbers, I don't know about you, but when I think whole number, I think of something that's not a fraction or not a decimal, but that is where English gets us in trouble. So the math definition of whole numbers, it's 0 plus the natural numbers. Okay. So basically the non-negative, non-fractions. Integers, well, we've had subtracted, multiplied, divided integers. We tend to think of integers being the negative numbers, but the integers are the negative numbers and the positive numbers and zero. And again, non-fractions, non-decimals. Sometimes for integers, you'll see a capital I or a fancy double I. So it's integers. Rational numbers. So rational numbers are any number that can be written as a fraction. So obviously that means fractions. Integers, you can make any integer a fraction by putting it over 1. And then decimals that terminate, which means the end, like 5.67. We can write that as a fraction because that 0.67 is 67 hundredths. So we can make that a mixed number, or that have a repeating pattern. For example, 1/3 is 0.3333 forever. So if they have a repeating pattern, that means there is actually a fraction that you can find to make it. No, there is no symbol for rational numbers. It's not R. We reserve that for something else. Irrational numbers are any number that cannot be written as a fraction, which basically, if you go on a number line, any two rational numbers will have an irrational number in between it and vice versa. So there's just as many actually there's more irrational numbers than rational numbers. When you go into that, you'll have to take a number theory class. But these are basically decimal numbers that never end and never repeat. The common example that most people are aware of is pi. And then a lot of our radicals are also going to be these non-repeating, non-ending decimals. So square root of 2, square root of 3, square root of 5. What you have to be careful of, though, is some radicals are rational, because like if you look at square root of 9, square root of 9 is 3, because 3 times 3 is 9, so that would be rational. And then what are real numbers? Real numbers are all your rational and irrational numbers together. And so all the numbers that we deal with on a daily basis are real numbers. And again, here the symbol is a capital R, or since I didn't have a script for it, a fancy capital R with a double leg in front of it. Okay. Let's get into, before I do any more definitions, let's jump into the homework. Do a couple of homework problems. All right, now, one thing I do want to point out, I don't know if I pointed out before, if you're doing past due homework, which by the way, there was a couple of days last week where the 6.4 is past due and wasn't open. Apologize. Somebody emailed me and let them know that that was the case, and so I got it fixed. But if you go on to past due homework, that's not going to do it, is it? Let me try something else. Okay, so if you get into a past due homework, if you're trying to finish it, do not do review and practice. Make sure you do improve score. If you're doing review and practice, that sounds exactly like it says. And if you see that note above it, it says it will not change your score. All right, so like if you're, say, studying for a test and you've already got a homework assignment done, then you can do the review and practice if you want. But if you are trying to catch up, get a past due assignment done for the homework, make sure you click that improve score. All right, so let's look at a couple of homework problems from 2.1. All right, so fill in the blank. So the resulting statement is true. So the set California, Colorado, Connecticut is expressed using, those are the roster method, set builder, or word description. Well, word description is a sentence, so it's not that because we have the curly brackets. I haven't talked about set builder notation. We'll come back to that. But this is, the set is in curly brackets separated by commas. That's roster method. So I probably should have done set builder notation, explain that. So I'll come back to set builder notation. All right, so like here's all the rational numbers. So this is sort of a problem you'll see. So they give us the set of several numbers, right? And then we're gonna see which ones are natural, which ones are whole numbers, etc. So what are natural numbers? Well, natural numbers are positive, non-fractions, non-decimals. So if you look at that, you may think there are none because those two are negative. 0 is not positive, it's a decimal. Square root of 5 is, here's where you have to be careful with your square roots. If you do square root of 5 in your calculator, well, if your calculator gives you back square root of 5, you need the decimals, hit that double arrow. And so that's like 2.23. So that's a decimal number that goes on forever. 4.6 is a decimal. Now, if you do square root of 121, gives you 11. So square root of 121 is actually a positive whole number. So how do you put that in there? You would do square root of 121. Yeah, so if you go in your calculator and it gives you the radical back, that's telling you that it is an irrational number. But if you put in the calculator and gives you a whole number, then you have a natural number as an answer. So out of all those, that's the only natural number. So what are whole numbers? Whole numbers are the positive numbers, natural numbers, and 0. Well, 0 is on that list, so now we got to do 0. And don't forget to include the whole number of, or the natural number of the square root of 121. And if you got more than one answer, put the comma between them. So basically, like natural numbers is part of whole numbers is part of integers. Integers are positive and negative, non-fractions. So now we have -2. And then our whole numbers of 0 and square root of 121. Okay. What are the rational numbers? Rational numbers are anything that can be written as a fraction. So all our previous answers plus anything that can be written as a fraction. Well, we have -5/6. That 0.23 is a decimal number that ends. That 4.6 is a decimal number that ends. So we have 3 new answers. With -5/6. And watch out for your commas when you're dealing with fractions. We have 0.23. We have 4.6. And then we got to put all our answers that we had before. So the -2, 0, and square root of 120. So completeness. So like most of these sets get bigger and bigger as you go. So because you're adding, like bigger umbrella, basically. So irrational numbers. Well, irrational numbers are things that cannot be written as fractions. So that's, are there any answers that we did not include? So square root of 5. And again, if you're going to calculate it, that's going to be one of those decimal numbers that goes on forever. So if it's not rational, then it's irrational. Now, what's a real number? I'm not going to write that one out because every single one of those is a real number. Okay. So those are some of the types of questions you might see. All right, how about this? Collection, is it well-defined or not? Because if it's not well-defined, it's not a set. So collection of U.S. airports. I know that seems pretty straightforward to me. So it's well-defined. Collection of the 5 best MLB is Major League Baseball. So is that well-defined? Well, here's the problem. What's best mean? There's no way you're going to get a group of people who follow baseball that are going to agree on what best is. So that is definitely not well defined. Write a description of the set. Okay. So this, so if you don't know, so I know those are zodiac signs. Honestly, I don't know what those begin with. So I don't know if B or C is reasonable answer. But here's what I do know is they both begin with S. I don't know if any of the rest of them begin with S. So this is sort of question that is a fair game, I guess, on homework, because you could look it up, your zodiac signs. I would not put a question like this on the test because that requires information that you would have to look up if it's kind of specialized. So I'm just curious here. Yeah, okay. So I guess there are no other zodiac signs that start with S. Okay, write a description of this set. 10, 11, 12, 13, dot, dot, dot. Okay. So it's not the first one because the dot, 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 because it's more than just those numbers. Okay. Is it all rational numbers greater than 9? All natural numbers greater than 9, all natural numbers. All right. So let's do with rational. So one of the things you have to do is pick out the difference between these. So C and D are talking about natural numbers. D is talking about rational. So what is a rational number? Anything that can be written as a fraction. We're not, they didn't give us any fractions, so it can't be B. So is it all natural numbers greater than 10 or all natural numbers greater than 9? Well, what's the difference there is where do we start, 9 or 10? So since it didn't say all natural numbers greater than or equal to 9 or including 9, then 9 is not part of the set. So D is the answer. If it was part C, our answer C, then we'd start at 11 because it didn't say to include 10. So again, when you're dealing with these sets, be careful with your starting and ending numbers. Yeah, let's see if there's any more I want to cover here before we run back. All right, yeah, so let's do one more and then we'll go back to the notes. All right, so write a word description. So it starts at 15, 16, 17, goes up to 29. All right, so sometimes it's easier to just kind of go one by one and eliminate them or maybe come back to them. So a set of all natural numbers between less than or equal to 29. So that less than or equal does include 29, but this doesn't work because it says all natural numbers. So natural numbers start at 1. This doesn't start at 1. The set of all natural numbers strictly between 15 and 29. So here's where, look at B versus C. So B just says between 15 and 29. C says greater than or equal to and less than or equal to. Okay. So I don't know about you, but that's looking like C. Definitely not B, because that would start at 16 and end at 28. Can't be D because it says all natural numbers greater than 15. So 1, it wouldn't include 15, and 2, it would go on forever and not stop at 29. And then why is it E, or why is it C and not E? Because here it says all numbers. So that includes decimals and fractions. We're not dealing with decimals and fractions. So that's why it's this is what you're going to have to do for this unit is know your definitions and be precise in what the language that you're dealing with. All right. So let's go back to the notes for a bit. Okay. So when we're talking about sets, so there's 3 ways to write sets. One is in sentence form, right? That's when just write down words. It's not very mathy. 2 is the roster form. So we've talked about that. So the roster says it's a list of elements that are, brackets are on the outside. Elements are separated by commas. Order doesn't matter unless Math Lab specifically says it does. And in general, we don't, it's considered improper list repeats. All right, so for example, that listing repeats, like if I was doing a poll of a class and I was listing like their birthday, and so like the set that I was talking about was this, days, birthdays. I would, 2 people had a birthday on May 2nd. I wouldn't list it twice because that's the same day. Which reminds me, there was a word I skipped. So universal set, which is going to be a capital U. So the universal set is like the overall set that all elements could potentially belong to. So universal set is like the universe or like an umbrella, where like if I had, so for example, often what happens with universal set, you may have like sets A, B, and C, where A may be like people who like OU Sooners, B might be the people who like the Cowboys, so U might be a set of all college football excuse me, all college football fans. So those sets A and B would be in this group. Or for example, if I was trying to write a universal set for like all my survey students, I could say, well, I could make that my universal set. I could say, it's all my students in math 1413, or it could go bigger. I could just say all call Albert math 1413 students, or I could go even bigger. I could say all call Albert students. So you could kind of keep getting bigger and bigger in your umbrellas, but you have to be careful because, for example, if I was talking about where people were born, I couldn't necessarily say that all my students are in the set of being born in Oklahoma because I know I have a couple of students that are born in Arkansas and other places. So those people would be outside that set. So the universal set wouldn't be big enough. So when we talk about universal set, it's always the umbrella that everything has to fit under for our set. Okay, so let's go back to the way we write sets. So the last one, and this is one that's going to be new for almost everybody, something called set builder notation. So anytime you have set builder notation, well, it's a set, so it's going to have the curly brackets. You're always going to see an X, and you're going to see a vertical bar. The way you read this is the set X such that, so that little vertical bar means such that. And then you're going to have some rule. So the important part as a student on set builder notation is getting that rule correct. That's really going to control the elements. But if you're writing set builder notation, you have to have the overall form. So you have to have, the set X such that, and you have to have the open and curly brackets. So you always have to have that in every set builder notation, and then you add in whatever the rule is. The rule is it could be, natural numbers greater than 5. It could be all integers. It could be X is the days of the week. So that rule changes from problem to problem. This notation, the set X, such that is an all set builder notation. That is definitely the mathiest form of the ways to write these sets. So what you're going to have to do is put sets in roster form and in set builder notation. And again, MATLAB's going to be multiple choice in a lot of this. Let's practice but not multiple choice. So let's look at 13. We're putting this in roster form. So it's a set of integers greater than 0 and less than 4 inclusive. Okay. For integers, we're dealing with positive and negative numbers and 0. So it says greater than 0, less than 4 inclusive. So where do we start? Do we start at 0 or do we start at 1? Because 1 is greater than 0. That word inclusive says we include 0 and 4. We'll start at 0. We're doing integers, so we're not doing fractions. So 1, 2, 3. That would be the roster form of that. Okay, what about 15? How do we read this? It's the set X such that X is a negative multiple of 10. So sometimes when you're doing set builder notation, you just got to kind of figure, when that rule is stated, you just got to figure out what you're talking about. So negative multiple of 10. Well, what are my like positive multiples of 10? 10, 20, 30, and so on. All right, but now we want them negative. So negative 10, negative 20, negative 30, and so on. And now we put that in roster form. Let's just put brackets around it. Or if you want to go in order from left to right, you could do dot, 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 and then negative 30, negative 20, negative 10. Right, in set builder notation. Okay. So what is this set? It is a single number 2. So if we're writing this in set builder notation, you need the set x such that. Now we need to know the rule. What is the rule? Well, the only rule we have is that x has to be equal to 2. So just say x equals 2, and then close your bracket. Okay. So what about 18? Sometimes you have to do some pattern recognition with this stuff. So I'm doing 24, 30, 36, 42, 84. This one, we do a lot of multiples of numbers. So when you look at 24, 30, 36, 42, hopefully you recognize this multiples of 6. So that's 6 times 4, 6 times 5, 6 times 6, 6 times 7, 84. If I do 84 divided by 6, I get 14. So how do we write that in set builder notation? Well, it's a set x such that, well, x is a multiple of 6. And so we can't just say multiple 6 because that would be, 6, would be 12, would be 18, and so on. How do we get the endpoints? Well, what I would do, I think the most efficient way to do the endpoints would say 24 is less than or equal to x is less than or equal to 84. I'm going to close bracket. Because if you put the less than or equal to, that means I'm including 24, I'm including 84. Now, this by itself, 24 is less than or equal to x, which is less than or equal to 84. So it's a bit messy. I ran out of paper. That would be like 25, 24, 25, 26, 27. Could be decimals, could be fractions, but also say it's a multiple of 6. So that rule sometimes in the set builder notation can be messy. For example, 19, the set of all cars owned by students. Okay, I had no idea how I'm going to figure all that information out, but sometimes you don't have to. So here's how I would do number 19 in set builder notation. It's the set x such that x is a car owned by a student. So sometimes you can take that sentence form and just rewrite that as your rule. Now, we're not going to let you get away with that with the mathy stuff. But something like this, that would also be acceptable. Good. All right. So here's what I'm talking about, just being able to recognize the sets, like write a description of that set. So 4, 12, 4, 8, 12, 16, 20. What do you know about those? Well, those are multiples of 4, and it never stops. So I would say this is multiples of 4 greater than or equal to 4. What about this one? This is the E is the set X such that. So what does that mean? Well, that's the symbol for element. That is, it might be hard to see, but that's a capital I. That says X is an element of the integers. So that means it's a positive or negative whole number. And -2 is less than X, which is less than 6. So what numbers are we talking about? We know we're not dealing with fractions or decimals, because otherwise it would say rational. So from -2 to +6, we're not including -2. So that means we're starting at -1, 0, 1, 2, 3, 4, 5, and then we include 6 because it's equal. So the description of that set would be the number, the integers from -1 to 6, including, inclusive. Or you could just restate that. It would be the integers that are greater than -2 and less than or equal to 6. Again, I'll bring up MATLAB and show you the wording on that. Okay, one more here. So we're going to write the description of the set Monday, Tuesday, Wednesday, Thursday, Friday. So that looks like weekdays to me. That's it. All right. Okay, so here is a definition that gets missed a lot, the cardinality of a set. So going back to my page where I have everything written out, it's number 15. So the cardinality of a set is the number of elements, I should say distinct elements, the set contains. And that distinct is important because basically it means we're not counting repeats. And so the notation, and this is where it gets missed on test all the time because students don't get the notation down. It's in parentheses of A or B or whatever the set is. So the way I read this, that's the number of A, basically. So the number of elements in A. All right. Let's practice that. So find the cardinality of set A. So on the first one, it says how many elements are in this set? Well, there's 1, 2, 3, 4, 5. The way we would answer that question would be the number of elements in A is 5. What about number 25? A is the set X, such that X is a month in the year. Well, how many months are in the year? There are 12. So the number of A would be 12. What about seconds in a minute? Well, there's 60 seconds in a minute. So the number of A, or the cardinality of A, would be 60. Now, numbers, again, can be a little tricky. So we're dealing with the set X, such that X is a natural number. So we're dealing with positive, counting numbers. And 15 is less than or equal to X, which is less than or equal to 23. So how many elements are in that set? Here's where you have to be a bit careful because you might want to just subtract them. If you do 23 minus 15, you get 8. But here's the problem. If you actually list them out, 15, all the way to 23. And now if you count them, you got 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, so if you're looking for the number of elements in a set, when we're dealing with numbers like this, don't just, well, first of all, you got to make sure you know what the endpoints are. So because of the equals, I know 15 and 23 are both included. All right, now if you subtract them, you're not counting either the top or the bottom. So if you're going to try to find the number of elements by subtracting, you always need to add 1 to make sure that you're counting correctly. So if we subtract them, we got 8, but there are 9 elements. So 8 plus 1 is where we get 9. It kind of shows it a little bit better on the next one. So if you look at 100, 101, 102, so 103, 104, and so on, up to 1,000, how many elements are in that set? Well, if you subtract 1,000 minus 100, it's going to give you 900. So if you try to say there's 900 elements, well, look at it this way. Let's say we start at 101. Well, that's at 1, and then 2, and then 3. So there are 900 elements right there, but then you have the 100 as well. There are actually 901 elements in that set. If you have a smaller set, my recommendation is write it out. It's like if 15 and 23 wasn't included, then we wouldn't have 15 and 23, it'd just be 16, 17, 18, 19, 20, up to 22. And then you can just count. All right. So make sure you know that notation. That's a big reason why people miss these questions on the test because they don't learn the symbols to go along with the definitions. All right. Let's back up to some more definitions. Like I said, there's a ton of them in this first section. And so sets are equivalent and equal. Now, if you're thinking in non-math terms, you may think these mean the same. Math terms, they definitely do not. I mean, they're related, but they are definitely not the same. So equivalent sets have the same number of distinct elements. So when in notation wise, number of elements in A is equal to the number of elements in B. So equivalent means they have the same number of elements. If they're equal is stronger than equivalent. Equal says they have to have the same exact elements. So equivalent just means they're sort of related, kind of, because it's this one has 3 elements, this one has 3 elements, this one has 1,000 elements, this set has 1,000 elements. Equal is extra. And so, if they're equal, they're also equivalent. It's just they have the extra. And anytime we put a slash through something, that means not equal to, or earlier with the element symbol, if we say it's not an element, that's what the slash is for. All right. And one last definition, and we'll go back to MATLAB. So the empty set or the null set is a set that has no elements. It's empty, or null is nothing. And so there's two symbols for the empty set. One, people often mistake for zero because a lot of people I think put a slash through their zero, or you can have brackets with nothing in them. It's the empty set. So one thing you have to be careful of is make sure that for your zeros, it's a zero. If we put a slash through it, then we are saying empty set. Okay. Let me give you a good example of an empty set. So a good example of empty set is if I'm talking about the ages of my students, and I want to list all my students who are over 100 years old. I have no students that are 100 years old, so that would be an empty set. Or let's say I want a list of the days of the week. Let's start with a Z. There are no days of the week, so let's start with Z. So that would be an empty set. And how many elements are in an empty set? There are zero because there are no elements. All right, let's do some of this equivalent versus equal. Good. All right, so 31. Are those equal, equivalent? Then we'll also say both or neither. So let's start with equivalent. Are they equivalent? This has two elements. This has two elements. So they are equivalent. Are they equal? Well, this has a 3. This has a 3. This has a 41. So does order matter? No. These are both equivalent and equal. All right, what about the next one? Break and break. Now, when I look at that, I would say they're only equivalent because I look at that, there is one word in the first one word in the second one. So there's one element in each. The words are, they sound the same, but they're written different. So those are not equal. So I would say only equivalent. Now, you got to be careful. The reason I put this in here, because I think I've seen this in MATLAB. Hopefully they fixed it. We'll see. One thing that they do in MATLAB, they kind of imply that there's commas between the letters. And so if there's commas between the letters, and it's not just a solid word, well, there's 5 letters here, 5 letters here, so they'd be equivalent. Then B and B, R and R, so then they have the same letters. So if there was commas between those, it would be both equivalent and equal. Because there's 5 elements of both, and the letters are the same. Right? What about the next ones? First, second, third, A, B, C. Well, they're definitely not equal. Yes, first, second, third is not the same as A, B, or C. However, they are equivalent. Yes, here's 3 elements. Here's 3 elements. Okay. All right, what about 34? 2 and 15, 2, 0, and 15. If you're thinking either equivalent or equal, then you're counting 0 as nothing that doesn't count. You gotta be careful of that. So because of that 0, these are neither. Because this one has 2 elements, this one has 3. So they can't be equivalent. If they're not equivalent, they can't be equal. Because that one doesn't have 0. The other thing to watch out for in MATLAB, what about 30? Are those equal, equivalent, both, or neither? Well, they both have 4 elements, so they're definitely equivalent. Are they equal? Well, in MATLAB, case matters. So since these are uppercase, these are lowercase, these are not equal. They're only equivalent. So uppercase, lowercase does matter to MATLAB. All right. So let's get back into MATLAB and see how some of these problems go. Let me just skip around a bit. Okay, so how about this one? So this is the set X such that X is an element of the natural numbers. See, you're going to have to, learn to read that. And so when it says it's an element of natural numbers, I now know that I'm dealing with only positive, like non-fraction, non-decimals, and X is less than 7. So that means it's not equal to 7. So when I'm down here looking at my list, B and C, I'm automatically going to discount because they include 7. I'm also going to discount B because it has negatives. Natural numbers are not negative. So now, is it A or is it D? Well, A has 0. Is 0 a natural number? No, it's a whole number. So this is why I say you have to know how to know your definitions so that you can apply. Okay, a set that contains no element that's empty or null and is represented by either the 0 slash to it or the brackets with nothing in it. Don't combine them. Don't put them together. It's either one or the other, not both, for the empty set. I guess I'd be checking this. All right. So determine if the set is empty. X or a set X such that X is a planet or solar system that begins with the letter D. Okay. There are unless I'm really missing something, there are none. Oh wait. I meant to put empty set. I'm not, so slow down. I got in a hurry. I knew there was no plans to start with D, so that should have been empty set because there's nothing. Okay. Is this an empty set? X is a number less than 2 or greater than 7. So if that said and, there is no number that's less than 2 and greater than 7. But the or says it can either be less than 2 or it can be greater than 7. There's a lot of numbers that are less than 2. There are a lot of numbers that are greater than 7. The or says, I don't care. It doesn't have to belong to both. It just belongs to one. So that is not empty because there are numbers that are less than 2. Okay. What is that little funky looking E symbol for? It's an element. So you start to get a feel, hopefully, for like how these questions are different, how this chapter is going to be different. There's a lot of true and false, which I'm not normally big on true and false, because it's kind of, I really wish what they would do is they would have us, if it's true or false, write down your reason. But MATLAB can't really do something like that. The reasoning for all these true and false goes back to your definitions. Okay. So determine whether or not the given statement is true or false. 12 is an element of the set 6, 8, 10, 12. Well, it's true because 12 is an element in that set. So the next one, true or false. 18 is an element in that set. So 18 is in there, so it's true. So it's either A or B. Now, again, this is where MATLAB is trying to do conceptual stuff. Is a natural number. Can't be not a natural number because 18 is a positive number. So you're going to have to kind of slow down and think about some of this stuff. And again, know your definitions. Okay. How about this? Is this true or not? 26 is an element of the set X such that X is a natural number. So it means it's a positive one. And it's 14 is less than or equal to X, which is less than 28. Well, 26 is positive. It is between 14 and 28. So that would be true. Example of this being false, if they said, is 28 an element of this set? Well, it would be false because there's no equals on the 28. Find the cardinal number of this set. D is the set 10. So how many elements are in that set? Don't say 10. It's a number of elements. There is only one number there. So the number of cardinality is 1. All right. So find the cardinality, cardinal number of the set 9, 12, 15, up to 45. All right. How are we going to find the number? Now, cardinal number is number of elements. So how are we going to find the number of elements? Well, it's going to be a bit tedious. My recommendation, write out all those elements. It's going to be 15, 18, 21, 24. So write them all out, count them up. That's going to be the best way to find the cardinal number on something like this. If it was 9, 10, 11, 12, 13 single numbers, then you could do 45 minus 9 and add 1. But since we're dividing, going by threes, that makes it a little bit more complicated. All right, find the cardinal number of the set given below. So it's set X, that should X is a continent. His name begins with the letter R. So again, this wouldn't be a good test question. So you got to know geography to this. So I got North and South America, Australia, Africa, Europe, Asia. I feel like I'm missing something. I'm not thinking of any of them that come with R. So since there's none that start with R, the cardinal number would be 0 because there's no elements in that set. Okay. Again, two sets that contain the same number of elements are equivalent. Okay, oh, this is a good one. Okay, so we have, are they equal? Are they equivalent? All right, so first of all, are they equivalent? So we have the set 10, 10, 10, 11, 11, 12, 13, 13, and then 13, 12, 11, 10. Are they equivalent? So what does equivalent mean? That means they have the same number of elements. So the question is, how many elements do they have? Well, B is the quick one, so it's 1, 2, 3, 4. How many elements does A have? Well, if you say 1, 2, 3, 4, 5, 6, 7, 8, you're going to miss this one because remember, for cardinality, we don't count repeats. So there's a 10, 11, a 12, a 13. Those are the distinct ones. So there's also 4 elements in A. They are equivalent because the number of elements in A is equal to the number of elements in B. Now, are they equal? Well, we already said don't list repeats. So kind of like take those repeats, cross them off so you're not even looking at them. This one, A would be 10, 11, 12, 13. B would be 13, 12, 11, 10. So what does that mean? Well, what it means is, do you know the definition of equal, which equal says they have the same exact elements. So do they have the same elements? Yes, because order doesn't matter, repeats don't matter. They are equal. Now, don't put the bottom one because it says the cardinality is the same. Remember, equal says they have to have the same elements. So to be equal, it would be answer A. Like I said, if you're going to be successful in this unit, you're going to have to learn your definitions and be able to apply them. All right. So I think that gives you a good overview of the homework. Like I said, in the Blackboard lecture notes, I have posted that handout with all the definitions. So hopefully that will help. That way all your definitions are in a couple of pages. And so just remember, for the rest of chapter 2, please learn your definitions. Please learn your symbols that go along with the definitions. And like every single time you have a question, if you don't know how to answer it, go back to the definition over and over and over again. Right? So that's how you're going to be successful with this chapter 2 material. Okay. Have a good day.